The quotient rule. When we have a rational function whose denominator cancels out, finding the derivative is very easy. But what happens if the denominator does not cancel out, as shown in the case below? We have f of x is equal to x cubed minus 2x plus 5, all divided by x squared minus 3. For these cases, we will learn another rule for finding the derivative of the quotient of two functions. If two functions u and v are differentiable, then the derivative of y is equal to u divided by v is that y prime is equal to u prime times v minus u times v prime. In words, the rule is the derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. Let's try an example using the quotient rule. Y is equal to 2x cubed plus 5x minus 1 all divided by 3x to the fourth. Find y prime. The first step is to identify our u, v, u prime, and v prime. U is our numerator, so 2x to the third plus 5x minus 1. Its derivative is 6x squared plus 5. Our bottom is 3x to the fourth, and its derivative is 12x to the third. Now we can apply these pieces to the quotient rule. Remember that our quotient rule is the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So our derivative of the top is 6x squared plus 5, and our bottom is 3x to the fourth minus the top 2x to the third plus 5x minus 1 times the derivative of the bottom all over the bottom 3x to the fourth quantity squared. And if we now distribute and multiply these, we get 18x to the sixth plus 15x to the fourth minus 12x to the sixth minus 60x to the fourth plus 12x to the third, all divided by 9x to the eighth. And then we have two terms that contain an x to the sixth, and when we combine them together, we get negative 6x to the sixth. And for x to the fourth, we have two of them. We have positive 15 and negative 60. When we combine them together, it's negative 45x to the fourth, and we have the 12x to the third that we're adding at the end, all divided by 9x to the eighth.